Welcome back to the deep dive. Today, we're tackling something invisible, but absolutely essential. It's the basis for, well, almost everything from how atoms hold together to why you get a shock from a doorknob.
That's right. We're talking about electrostatics, the physics of electric charges when they're just sitting still.
Or mostly still, anyway. And our goal today, to really get under the hood of this, we want to give you a solid handle on the core ideas. Charge, force, fields, potential, all that good stuff.
Exactly. We've got some detailed source material here focusing on the fundamental laws, but also packed with some pretty surprising facts and real-world examples. We wanted to distill that down for you.
Okay, let's dive in. Where do we start? Probably with the absolute basics, the electric force itself, and what charge actually is.
Right. The number one rule, the one that governs pretty much all interactions at this level, is beautifully simple. Opposites attract, likes repel.
Positive charges attract negative charges. Two positives push each other away, two negatives push each other away.
Precisely. And this simple push-pull, it's not gravity, it's the electric force. And it's what holds matter together. It's why atoms form molecules and why those molecules make up, well, everything, including us.
So digging down a bit deeper, who are the actual players, the subatomic particles doing the attracting and repelling?
Okay, so you've got three main characters here.
Yeah.
You have the electron, which carries a negative charge.
Right.
Then the proton, carrying a positive charge. And the neutron, which, like the name suggests, is neutral, no charge.
Okay, proton positive, electron negative, neutron neutral. Got it.
But here's a really key detail from our sources, something that makes a huge difference. The mass.
Yeah.
An electron and a proton have charges that are exactly equal in magnitude, just opposite in sign.
Okay.
But the proton, it's roughly 1,800 times heavier than the electron.
Whoa, 1,800 times.
Yeah.
That's a massive difference. So does that mean the protons are basically stuck wherever they are in everyday situations?
That's exactly it. Protons are locked deep inside the atomic nucleus. They're the heavy anchors. It's the electrons, being so incredibly light, that are easily moved around.
Ah, so when we talk about static electricity, like rubbing a balloon on your hair, it's always the electrons doing the moving.
Almost always, yes. It's the electrons being stripped off one surface and transferred to another. And this also explains why most big objects you encounter are electrically neutral.
Because they have an equal number of protons and electrons, so the charges cancel out.
Precisely. A perfect balance, resulting in a net charge of zero. But crucially, charge isn't something you can just, magic into existence.
Right. There's a fundamental rule about that, isn't there?
Yes, the conservation of charge. It's a bedrock principle. You can't create net electric charge, and you can't destroy it. All you can ever do is move it from one place to another.
Like shuffling electrons around. The total amount of positive and negative charge in an isolated system stays constant.
Exactly. Think of it like money. You can move it between accounts, but the total amount doesn't change unless something comes from outside the system.
Okay, so we know charges attract or repel. The next big question has to be, how strong is that force? How do we actually put a number on that push or pull?
Now we get to the famous equation, Coulomb's law. This is what lets us calculate the force, let's call it F, between two charges.
And the equation is $1 equals K Q1 Q2 to 2.
That's the one. And it tells us two incredibly important things right away. First, look at the growth one and two $2 on top. The force is directly proportional to the product of the two charges. More charge means more force.
Makes sense. Bigger charges push or pull harder. What about the D on the bottom, the distance?
That's maybe the most critical part for understanding how it behaves. The force is inversely proportional to the square of the distance between them.
The inverse square law, just like gravity. So if you double the distance,
The force drops to 1/4 of what it was. Triple the distance, it drops to 1/9. It falls off fast.
which explains why, you don't usually feel the static electricity from something across the room. It's really a short-range powerhouse.
It dominates at atomic and molecular scales, absolutely. But there's another piece here, the constant K.
Right, the Coulomb constant. What's the value on that?
It's huge. It's $9 times 109 m 2c2c, $9 billion Newton meters squared per Coulomb squared.
9 billion. That's enormous. What does that number actually tell us?
It tells us that the electric force is intrinsically, fundamentally, unbelievably strong. Compared to the gravitational constant, GK is vastly larger. If you somehow manage to get just 1 Coulomb of positive charge and 1 Coulomb of negative charge separated by 1 meter.
Which we should probably clarify. A Coulomb C is the unit of charge, and it's actually a massive amount of charge, isn't it?
Oh, absolutely enormous in everyday terms.
Yeah.
1 Coulomb is a charge of about $6.25 times 1018 electrons. That's 6.25 billion electrons. You don't get coulombs of charge just by rubbing things together usually.
So back to your example. 1 coulomb positive, 1 coulomb negative, 1 meter apart. The force.
The force of attraction, according to Coulomb's law, with that huge K, would be 9 billion newtons. That's enough force to lift multiple battleships.
Just from 1 coulomb, that really puts the strength of this force in perspective compared to gravity.
It completely dwarfs gravity at the level of individual particles. Gravity only wins out on the scale of planets and stars because those massive objects are, overall, electrically neutral. But where you have separated charges, the electric force rules.
Okay, fascinating. So we have the force law. Now, let's talk about how charge moves or doesn't move through different stuff, materials. Why are some things like metals great at conducting electricity while rubber or glass just stop it?
It all comes down to how tightly those electrons we talked about are bound to their atoms. In conductors, like copper or most metals, the outermost electrons are really loosely held. They're often called free electrons.
So they can just wander through the material easily.
Pretty much. They form a sort of sea of electrons that can flow readily if you apply an electric force, which is what we call electric current.
And the opposite.
Those are insulators. Think glass, plastic, rubber. In these materials, the electrons are bound very tightly to their individual atoms. They just won't move easily. They resist the flow of charge.
Okay. Conductors let charge flow, insulators block it. Are there materials in between?
Yes, and they're incredibly important. Semiconductors like silicon and germanium, they're kind of halfway houses. They can conduct electricity, but not as well as conductors. And crucially, their ability to conduct can be controlled very precisely.
And that control is the key to all our modern electronics, right? Transistors, computer chips.
Exactly. They are the foundation. And there's one more category our sources mention, superconductors. These are materials that, below a certain critical temperature, offer literally zero resistance to electron flow. Amazing stuff, but usually needs very cold temperatures.
Right, okay. So we have different materials. Now, how do we actually get charge onto an object in the first place? How do we charge something up?
There are three main ways, and again, it's all about moving those lightweight electrons. The first one is probably the most familiar, friction.
Like rubbing a balloon on your sweater.
Exactly.
Uh,
When you rub two different materials together, sometimes electrons get scraped off one surface and stick to the other. One object becomes positive, lost electrons. The other becomes negative, gained electrons. That's your basic static cling.
Okay, friction. What's next?
Conduction. This is charging by direct contact. If you have a charged object, say a metal sphere with extra electrons, and you touch it to a neutral metal sphere,
The electrons will spread out onto the second sphere.
charge flows from the charged object to the neutral one until the sort of electrical pressure is equalized between them. Simple contact transfer.
And the third method, you said it was clever.
Ah, yes, induction. This is how you can charge an object without touching it with another charged object. It's a bit more subtle.
How does that work?
Okay, imagine you bring a negatively charged rod near, but not touching, a neutral metal sphere. The free electrons inside the neutral sphere will be repelled by the rod and will move to the far side of the sphere.
So one side of the sphere becomes slightly positive, lacking electrons, and the other side becomes slightly negative, excess electrons.
Exactly. Now, while the rod is still nearby, if you briefly connect the sphere to the ground, just touch it with your finger or connect the wire to the earth.
The excess electrons on the far side have somewhere to go.
Precisely. They flow off the sphere into the ground, then you disconnect the ground wire, then you remove the charged rod. The sphere is left with a net positive charge because it lost some electrons. You charged it without direct contact.
That is clever. But hang on, there's something related here I wanted to ask about. You know how a charged comb can pick up little bits of neutral paper? The paper is neutral overall, right? So why is there an attractive force? It feels like Coulomb's law should say zero force.
Ah, great question. This is electrostatic polarization. Even though the paper bits are neutral, the molecules inside them can get distorted by the nearby charged comb.
How so?
Let's say the comb is negatively charged. When it gets close to a paper molecule, the electrons in that molecule might shift slightly away from the comb, making the side of the molecule closer to the comb slightly positive, and the side farther away slightly negative.
So the molecule becomes a temporarily little dipole, positive end and negative end.
Exactly. Now, because the positive end of the molecule is slightly closer to the negative comb than the negative end is. Remember the inverse square law.
Ah. The attractive force on the closer positive end is a tiny bit stronger than the repulsive force on the farther negative end.
Precisely. It's a tiny difference, but summed over all the molecules on the surface, it's enough to create a net attractive force, even though the paper itself is still neutral overall. It's a neat effect.
That really is neat. Okay, so we've talked force between charges, but physics often finds it useful to think about the influence around a charge, even if there's no second charge there yet. The field concept.
Right, the electric field, usually written as E. It's a way of describing the condition of space around a charge. It's like an invisible aura or influence.
So the field exists everywhere around a charge, waiting to exert a force.
Exactly.
Yeah.
We define the electric field at any point as the force that would be exerted on a tiny hypothetical positive test charge, if you place it there, divided by the size of that test charge. So $1 equals F B WASP.
And we draw lines to visualize these fields, don't we?
We do. Electric field lines always start on positive charges and end on negative charges. They show the direction of the force on a positive test charge, and how dense the lines are tells you how strong the field is.
Okay, fields describe the force potential. Now let's bring in energy. What's electric potential energy? PE.
Just like listing an object against gravity gives it gravitational potential energy, moving a charge against an electric field gives it electric potential energy. It's the energy stored in the system due to the position of the charge in the field.
So if I push a positive charge closer to another positive charge, I'm doing work against the repulsive force.
And you're increasing its electric potential energy, like
Yeah.
compressing a spring. It now has stored energy that can be released. If you let it go, it'll fly away.
And from potential energy, we get something we talk about all the time. Voltage. How are they related?
Voltage, or more formally electric potential V, is basically the electric potential energy per unit of charge. So VI used to cuke.
Energy per charge. What does that represent conceptually?
Think of it like electrical pressure or height. Potential energy is the total energy the whole collection of charge has, while voltage tells you how much energy each individual Coulomb of charge has at that specific point in the field.
And the unit for voltage is the volt V, right?
That's the one. 1 volt is defined as 1 joule of energy per 1 Coulomb of charge. So 1 V equals 1 JC.
So when my battery says 9 volts,
It means that every Coulomb of charge that moves from one terminal to the other delivers 9 joules of energy. Voltage represents the push, or the potential difference that drives charge to flow.
okay, fantastic. We've covered charge, force, fields, energy potential. Let's connect this back to the real world. How does understanding electrostatics help us or keep us safe?
Well, a classic example is lightning protection. Benjamin Franklin's lightning rod, the Parrot Tenaire.
How does that work based on these principles?
It uses the idea that electric charge tends to accumulate on sharp points. By putting a sharp, grounded metal rod high up on a building, it allows charge from the atmosphere to leak off gradually and safely to the ground, or provides a safe path for a lightning strike if one occurs. It neutralizes the buildup.
Preventing that massive sudden discharge we call lightning. Smart. What about everyday safety?
Static discharge is a big one, especially around flammable things. Our sources really highlight the danger when pumping gasoline, for instance.
Because sliding across your car seat can build up static charge through friction.
Exactly. And if you then reach for the metal gas nozzle, that tiny spark, harmless to you, could potentially ignite the gasoline vapors. It's a real risk.
So the safety advice is always to touch the metal body of your car before touching the pump nozzle.
Yes, that grounds you, discharging any static buildup safely before you get near the flammable vapors. A simple electrostatic principle saving lives.
It's amazing how these fundamental rules scale up from tiny particles to massive safety concerns. We've gone from electrons and protons to lightning rods and gas station safety.
It really shows the power of these core ideas: attraction, repulsion, charge movement. It underpins so much.
So as we wrap up, we've talked about how strong the electric force is compared to gravity. Here's maybe a final thought to leave our listeners with based on our sources.
Consider this. We know the electric force holds that tiny electron in orbit around a nucleus. But our sources also mention scenarios where an electron might have enough potential energy to jump across, say, a 5,000 volt gap.
5,000 volts. That's a huge electrical pressure difference.
It is. It represents a significant amount of potential energy per unit charge. Creating that kind of potential difference requires substantial work. So, here's the question. If it takes that much electrical height or potential to influence the behavior of a single, almost massless electron, how much energy, how much work is constantly involved at the quantum level, just keeping the universe structured the way it is, holding every electron in its place within atoms?
Wow. Thinking about the sheer energy investment in maintaining the structure of matter itself, all driven by these electrostatic rules. A really potent thought. Thank you for walking us through this electrostatics deep dive.
My pleasure. It's fundamental stuff.